This chapter should be pretty straightforward. We get to combine some of the material that we've learned in the past few chapters. Back in chapter 5, I believe, we did the discussion of estimation, where you take data that you've inputted in Excel or from some other source, and you're able to run regressions to come up with estimates of coefficients and intercepts and assess those things using R-squares, p-values, all that good stuff. Again, that was a discussion of bringing in data and being able to create equations from that data to describe that data. In chapters 8 and 9, the two previous to this one, we talked about production and cost in the theoretical sense, in the short run and in the long run. And we developed these graphs of the different curves, short run production, short run cost curves, and then same thing with the long run. And again, in those previous two chapters, it was all sort of at the level of theory. We looked at how these pictures were supposed to look, how these functions were supposed to look. What we're going to be able to do here in chapter 10 is to combine those and say, let's take data on quantities and the amount of labor and figure out a way to estimate production function from those. And let's take data on the quantities we've produced and the costs that we've incurred and estimate cost functions from those. So again, there are sort of two different types of production functions. In a general sense, this long-run production function described how output was related to the amount of capital and labor input. We didn't really describe it like this, but sort of a variation of the long-run production function is the short-run production function, where you say, okay, we know that output is generated by capital and labor, but as kind of a variation of that, let's hold the amount of capital constant, because in the short run that's true. In the short run, the amount of capital is constant. So this short-run production function, again, is kind of a variation on what the long-run production function is. So to describe how production behaves, if you think back, or if you look back at the production functions that we had a couple chapters ago, you notice that it had these two phases to it. It had the teamwork phase, where your output increased at an increasing rate, and then you had this crowding phase, where for a little while your output continued to increase, but at a decreasing rate. The total product curve started to decline, even though it still had a positive slope. And then you hit the point where marginal product was 0 and then became negative, and your total product curve actually started to tilt back downwards. And there's sort of two changes of direction, I guess, if you want to think of it. There's, again, the increasing marginal product range and then the decreasing marginal product range. And that's best, that description of what's happening is best described using this cubic production function. And again, if you go back to the chapter on estimation, you'll see a picture of what cubic production functions look like. And again, we're going to derive this short-run production function from the long-run function. The long-run function is still cubic in the sense that it has these terms that are to the third power. If you remember back, something to the second power is squared, something to the third power is cubed. And so we call this a cubic long-run production function. And again, you can see that output here, Q, is related to capital, K, and labor, L. And you have these two different coefficients to it. And of course, it's long run. We're allowing the amount of capital and labor to vary. Another thing you might notice that I think I may mention later on is that there's, well, two things. There's no intercept term here. There's no, usually when we had the equation like this, we had the A be the intercept. But there is no intercept in this case. And I'll let you think about why that is true. You also might include maybe a third term in here, plus C times K to the first power times L to the first power. You could do that too. And depending on what the coefficients look like and if they're significant or not, would tell you whether you should include those terms to the first power. But you at least would include a second power and to a third power. Okay, so our short run production function, again, will have sort of the same format as the long run function does, but we're going to hold capital constant. And so they put this bar over the tops. And since K is never going to change, then really those terms kind of get transformed so that the small a there and the K to the third power, those never really change. And in the second term, the B and the K squared terms, those never change either of those. And so you can kind of rewrite this as a capital letter A times L to the third, where capital A equals the little a times K to the third, K bar. And then this capital B, you could equate to little b times K bar squared. And so you can kind of rewrite this production function to this short run form of it. But I still see that I've got this L squared and this L cubed term. And again, if you wanted to throw an L term in there too with a capital C in front of it, you could do that as well. You get your average product, your marginal product terms the same way that we always do. Average product is just Q divided by L. So if you take that short run production function, divide it by L, you get AL squared plus B times L. Marginal product will be the derivative of the cubic production function with respect to the variable L. So 3 times A plus L squared plus 2 times B times L. To estimate these things, one little caveat that might not make a whole lot of sense right now is when we do regression analysis, we're presuming that the equation we're estimating is in a linear form. And right now we don't really have that because we have this production function with L squared and L to the third power. A linear regression would be your independent variables are always to the first power, and we don't have that yet. But we can modify things a little bit to turn it into a linear equation. So if we had an equation like this, Q equals A times X plus B times W, I can see that there's no squared terms, there's no cubed terms or anything like that. Everything is to the first power. If you also remember back, we redefined this capital letter A to be the little a times k to the third. We had this capital letter B that we redefined as little b times k squared. We can do sort of the same thing, and where you see this x and the w, we can redefine those too. And we can say this capital X will be our L to the third power, and capital W will be L squared. In Excel, you would have a column of Q, and you would have a column of your L, and if you just did a scatter plot of those, you'd see that short-run production function with, again, the teamwork phase and the crowding phase, 2 changes of direction to it. To run a regression, you could say, well, okay, I need to make 2 more columns because I want to describe this equation as a cubic functional form. So I want to have an L squared and an L cubed column. And so in Excel, you might, in your third column there, you might set that up to say, okay, that's going to be my L squared column. And you could just, do the little equal sign and refer back to your L column and then square that. So, L times L or L with the little caret symbol 2 to make it squared. So you could have a column of L squared, or you could call that column W if you wanted to. And then you make another column of L cubed, where you could refer back to your L column and do L times L, or L to the third power, or whatever. So you'd have a column of L cubed, and again, you could rename that if you wanted to. You could rename that X to be consistent with what we have here. So I mentioned before that there's no intercept term in this cubic functional form. You may have wondered why that is. Well, since this is production, then I wouldn't expect there to be any output at all if there was 0 labor input. And so, just by definition, we would have to assume that this production function has to go through the origin. So we don't want there to be any intercept term at all. And in Excel, you can have to look back at how it's specified, but when you pull up the regression, the window that pops up, you tell it what you want your x variables to be, what you want your y variables to be. There's that little box when you have the labels. There's also a little box that says you want it to go through the origin, or you want the intercept to be 0, something like that. So you can tell Excel that that's how you want it to be. Estimating the production side is fairly easy because you have Q, the amount of output, and you have L, the number of workers. So those things don't really change too much over time, or the interpretation of them don't change too much over time. When you're looking at the cost data, though, for estimating those cost functions, then you do have to worry a little bit because the cost data is in terms of dollars. And we have to recognize that dollar amounts differ over time. Obviously, if you talk to your grandparents, they'll tell you about how they could buy a can of Coke for 5 cents when they were a kid, and now it's 50 cents or 75 cents to buy a can of Coke. And so it's still the same can of Coke, though, but we recognize that the reason that the dollar amount is different is because of inflation. And so if you have cost data like this, a lot of times it's useful to be able to correct for the inflation that's happened, because again, inflation kind of messes things up. The interpretation is off a little bit. So what we would like to do is to get rid of the effects of inflation. And again, in economics jargon, the dollar amounts that you are just given that include the effects of inflation in it, we call those nominal dollar values, or nominal amounts, or nominal costs. Once you've corrected for inflation, though, then we call those, well, that's a real dollar amount, or a real value, or real costs. So we want to be able to correct for inflation. The way that we do that is we use what's called a price index, and you may be familiar with the consumer price index. It measures the change of the dollar value in purchasing a typical basket of goods that a typical consumer buys. So I kind of describe it to my principles class like this. You have a grocery list, and you buy everything on your list, and you see how expensive it is. You hold on to your list, and the next year or the next month, you buy everything on that list again. You're holding everything else the same. At the end of the day, though, the only thing that's not being held the same is the value of $1. You're still buying the same groceries, you're still buying the same amount of groceries, but at the end of that month or the end of the year, you probably wouldn't expect to pay the same amount for all of those groceries. And it's because the value of a dollar has changed. There may be individual prices of individual products that have changed for certain reasons, but all of that combines into kind of describing what's happening to the value of a dollar. So when we want to correct for inflation, we want to say, well, how much inflation has there been from one year to the next? And if we've constructed this price index in that way, by buying this grocery list every year or every month for several years, then you can get a good sense of how much inflation there has been between year A and year B. And that's my son coughing. So if we have this dollar amount, X dollars, and it could be, we had $1 million of cost last year or whatever it is. You have X dollars, and those were calculated or tabulated in a particular year A, and you want to convert that to another year B. You want to say, well, if we paid this much in cost 5 years ago, and we want to see what the equivalent value of that would be today. Well, your year A would be the 5 years ago year, and your year B would be today, and you have this whatever dollar amount that you want to convert. The equation that you use is to get your real value. You would start with the nominal value, X dollars, that you started with, and you would multiply it by this ratio of the price indexes. I rewrite it a little bit differently than the book does. The real dollar amount will be, again, the nominal dollar amount that you start with, and you multiply it by this ratio of the price indexes, where the numerator will be the price index the year you are converting to, that year B, and the denominator will be the price index for the year you are converting from, or the year A. So just as an example, let's say that in 2000, our advertising budget was $10 million, and we wanted to know, we got a sense of how much that bought us in terms of the amount of revenue that came in as a result of those sales. And we want to think about, well, let's spend an equivalent amount of money in 2010 as we spent back in 2000. So how much money would we have to spend now to give us an equivalent advertising impact, if you want to think of it that way? Well, you would need to know, what the $10 million is, that's the nominal value you're starting with. But you would need to know how much inflation there's been between the year 2000 and the year 2010. From the Bureau of Labor Statistics, which I was able to get before the government shut down, this is October 2013, we've had our little government shutdown, so none of our websites are working because the government's having its little temper tantrum. So I was able to get these consumer price index values before the government shutdown. So here's the CPI values annualized for those years. So I have my CPI from the year I'm converting from, the year 2000, and I have the CPI for the year that I'm converting to, the 2010 CPI. So I start with my $10 million, that's my nominal amount of money that we spent in the year 2000, and I multiply that by this ratio of the price indexes. So 2010's CPI divided by the year 2000's CPI, and I get a value of 12.66 million. So how would I interpret this? Well, the amount of money we spent in the year 2000 would be equivalent to $12.66 million of, well, 12.66 million 2010 dollars. Here's our short run cubic cost function, and we mentioned about converting nominals to reals before. Again, this will be cubic also. If you look back at what our chapter 9 picture of the cost curve looked like, this is the total variable cost curve. It had this cubic shape to it also. It had the teamwork phase early on with the costs slowing down, and then once you had the crowding phase, those costs started to pick up again. And so you had this cubic shape, so there's going to be a squared term and a cubed term in it. And they also include the q to the first power as well. And again, you can get your average variable cost, your marginal cost terms pretty easily out of those just by doing algebra and calculus. So like I said, this cubic specification makes this S-shaped total variable cost curve, and it also, when you do the algebra to get the average variable cost, and when you do the derivative to get the short run marginal cost, those things end up being U-shaped, and that's what a quadratic function looks like. And you'll see that the average variable cost, the short run marginal cost functions were quadratic. They had terms that were just q and q squared in them. Another nice thing is that you might think, well, geez, I need to know the total cost curve and the total variable cost curve, and I need to know the average variable cost and the average total cost and the short run marginal cost. There's like 4 or 5 different functions that we need to estimate. Actually, you don't, because they all rely on the same sort of intercepts. They all rely on the same parameters, the same coefficients. And so really all you need to do is to be able to estimate one of the equations, and you'll be able to get estimates of all of them. So if you have just your total cost data, then you can run a regression on that, and we didn't really talk about it in the previous slide. But the total cost function will basically be your total variable cost function, but there will be some positive intercept based on what your fixed costs are. And so if all you have is your total cost data based on your output, you have a column of Q's and a column of TC, then you can run a regression on that, and whatever the intercept is, that's your fixed costs. And then whatever the coefficients are for the Q and the Q squared and the Q cubed, you can use those to construct the other cost functions out of them. And we'll probably have one or two little assignment questions based on that. So again, just kind of summarize everything. On the production side, you start with this short run production equation where, again, A and B here, the capital A, capital B, include the fixed capital in there. And so Q equals A times L to the cubed plus B L squared. And again, if you wanted to, you could throw in a plus CL to the first power if you wanted to do that. Just dividing everything by L gives you your average product. Taking a derivative gives you your marginal product. And the book has these other things about being able to tell where diminishing marginal return sets in. You could figure that out if you wanted to. When you run the regressions on these things, you should notice that your A coefficient is usually negative and your B coefficient is usually positive. So if you want to keep those in mind, that's fine, those last two little points there. On the cost side, again, you start with this. They started with this total variable cost function, and again, you could do a total cost function, which would be basically the exact same equation here, but maybe throw a plus D. D would be the value of your fixed cost, the intercept. So you could have that. And again, using algebra, you can get your average variable cost out of it. Divide everything by Q. Take a derivative to get your marginal cost equation out of it. And again, the book includes a few other little factoids about how you're able to use the coefficients out of these equations. And it gives you a sense of what the parameters should be, whether they're negative or positive. So we kind of have everything we need now to combine the information about the theory of production and cost in chapters 8 and 9. And now we know how to construct those equations given the data that we've collected on our own company's cost or output.